So what we want to do next is review for the first exam. And I'm going to use the review document that I handed out. And I picked out some questions and highlighted the ones I want to be sure to get to. So you can pull out your copy and make a note of which ones that I've highlighted. I'm going to share mine, so it'll be on the screen.
So you're doing all the review tests that you gave us?
Yeah, off of the review. Yes, we're using that. There it is. Okay. So there are 205 questions in here. Not going to be nearly that many on the test. This is just a review to give you lots of practice if you have the time and the energy.
How many questions do you use?
I think this one has 86. Yeah, but a lot of them are just their memorization. Later on, when we actually have to take time to solve a problem, you know, it may take 5 or 10 minutes to do it, then I reduce the number of questions so that you have time to finish it all in a reasonable amount of time. It's not like I'm giving you an SAT. Or do you guys take the ACT? ACT, okay. They're all the same. They're meant to destroy your confidence if possible.
Work for me.
Yeah. Yeah, when I was I think I took it twice. I took junior and senior, the SAT. Okay, so notice that these are numbered for chapter 1 number sequence, and then when we get to chapter 2, it'll revert to 1, 2, 3. So what I need to do is chapter 1 here, so the number sequence can be followed. All right, for number 1, and the nice thing about the review is sometimes I come across these questions and I can't remember covering the topic in class. Right, so it gives me a chance to present this stuff. Which of the following is an example of a quantitative observation? There's one. Did I make a distinction between quantitative and qualitative? Probably not. Qualitative is simply a descriptive term, like the color is, or this item is bigger than that item, that type of thing. It's just not really measured. Quantitative is derived from, well, the same root as quantity, right? It's a measurement that has a number with it. It's a value. So with that in mind, you can go through that series and you can see that D, the temperature of a liquid is 60 degrees, is the one that satisfies. Okay. Then we have 2. Generally observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called what? Right. Remember the difference between a law and a theory. The primary difference between the two is why. Theory tries to explain why so that you can predict changes in the theory. Whereas a law simply says, under these conditions, this always happens. And I throw up my hands, I don't know why. So what we've got here is a situation where we're describing a natural law. Now we didn't put it in those terms, natural law, but that's what we're talking about here, right? It's not a constitutional law, right? It's a natural law. These things exist in nature, and scientists just describe them. They've been there from the very beginning, as far as we know. And then the natural law is just our attempt to describe what's happening. All right. So here are prefixes that modify base units so that we get a different number with a different base unit. Right? What we want to do here is order smallest to largest. What do these base units mean? And let me put it over here, 5. We've got nano, milli, and these are prefixes to base units. It could be nanometers, it could be milliliters, it could be anything as a base unit. These modify it in certain terms. Centi and kilo. So what does each one of these mean? This one means that you multiply the base unit by 10 to the minus 9. It's a billionth of. This one means you multiply it by 10 to the minus 3, or 1,000th of. This one, centi, is 10 to the minus 2, or 100th of, like centimeter. A centimeter is 100th of a meter. It takes 100 of them to make it. Right? It would be, that's a yardstick. Won't work. And kilo means you multiply the base unit times 1,000. Okay, so the question asks us, order them in smallest to largest. Right? They're already in order. Right? So A is the answer. They need to clean these boards with something else. Maybe furniture polish would work better. Okay, number 6. 8.1 kilograms contains how many grams? So here's where we're starting. Kilograms. And we want to convert that into grams. So this is a problem in dimensional analysis. The procedure that you develop for converting that is based upon the units of measure. That's what that means, dimensional analysis. So we want to end up with grams, so many grams. Well, we need something. We can multiply that times 1, but that won't get us anywhere. We need something that's equal to 1. So we need an equivalence. So what's equal to a kilogram? 1 kilogram equals 1,000 grams, right? Now, if we put kilograms under here or grams under here, we've got 1 either way. What we need to decide is, where do they need to go to get us from there to there? Well, we want to cancel that one. Right? Numerator, denominator. You got to cancel it. But then leave us with in the numerator, because that's where this one is. Okay. Then we put the equivalent value. This one is 10 to the 3rd. Right? 10 to the 3rd grams is 1 kilogram. So that means this one cancels, and 8.1 times 10 to the 3rd grams is 8.1 kilograms. All right, so B is the answer in this case. This thing doesn't want to close. There. Okay. That was 6. Got a 7? Yeah, we're doing a 7 also. Let's do it down here so we don't have to split it up. Convert 0.3980, 0.3980, what? Meters to millimeters. Okay. So these two problems are very simple. You can convert them with a single factor without chaining any factors together yet. So we want to cancel that one and leave us with this one. Right? So we just need to know what's the relationship. You can do it 2 different ways. if you know how many millimeters are in a meter, right, which is or how much of a meter, what does this mean right here? Milli. It means 10 to the minus 3, doesn't it? So we would have 10 to the minus 3 down here is equal to that one. So this part is equal to that part, and this part's equal to that part. That's one way to look at it. And if you divide that number by 10 to the minus 3, it's the same thing as multiplying by 10 to the third, isn't it?
10 to the minus 3 in there is
I'm sorry?
0.00.
Well, this is 1 millimeter is equal to 10 to the minus third meters.
Yeah.
Okay. What was your question?
10 to the minus 3, like, what is that? Because we've talked about kilo is 1,000.
Oh, 10 to the minus 3 is 1,000th of.
Okay, that's fine.
Yeah.
I want to say it. Sorry.
Okay. No, that's fine. Okay, so if we divide by 10 to the minus 3, it's the same as multiplying by 10 to the 3. So that would be, we'd move the decimal place 1, 2, 3. And that would be 398.0. Or A. Yeah, A is the best answer for that one. And this is significant, right? That 0 is significant, that 0 is not. So this number has 4 significant figures in it. And that number has 4 significant figures. All right, let's scroll to the next one. 9. This is just, you have to know it. What is the measure of resistance an object has to the change in its state of motion? Now, I didn't frame it this way when we went through the discussion. I just juxtaposed the difference between mass and weight. Right? Mass is a measure of how much substance there is. Weight is a measure of what force it applies in a gravitational field. But another way to express it is, if something has mass, that's the reason for Newton's first law of motion. An object tends to remain at rest unless acted upon, or it tends to remain in motion unless acted upon. So the thing that keeps it in motion or resists a change in motion, like this is stated, is the mass. Right? It's not the weight, it's the mass. And that is the basis for moving Newton from his first law to his second law. When he wrote F equals ma, there's the mass, there's the, and it's resisting a change in motion. But if we manage to apply an unbalanced force against it, then it will accelerate at that rate. So that's the long way of saying the answer is A, mass. And that's the thing that keeps everything on the table when the smart aleck grabs the tablecloth and yanks it out from under everything. And if you do it right, then the mass of all those items is sufficient to keep them from moving, as long as there's not enough friction between the tablecloth and your wine glasses. Right? If you pull it too slow, they'll end up on the floor. Or if you use a cotton tablecloth, it's not a good idea. You need to use something like polyester, right? Something really slick, silk. All right, number 11. All right, we have this data set where we've made the same measurement of a 1 gram mass, 3 trials. Sometimes we call those replicates. We've measured it 3 times, and with what we know about our measuring device, we can have confidence in that measurement that it's plus or minus 0.001, right? So it could be 1.201, plus 1 would be 2, and minus 1 would be 0. So it could be between 1.200 or 1.202. Between those two numbers, somewhere is the true number. And we do that with the rest of them. Like the second one would be between 1.201 and 1.203, or 1.199 and 1.201. Okay. Now, the question is, has to do with both accuracy and precision of those measurements. Now, first of all, are any of them accurate? No, no. The value is 1 gram, and our measurement is coming up with 1.2. That's way off. Like that's I don't know, 20% error. That is 0.2 divided by 1 times 100. So it's not precise. I mean, not accurate, excuse me, not accurate. How about precision, though? Precision just says, are they grouped close together? Yeah, they're really close together. So it's precise, but not accurate. Have any of you had statistics before? Okay. So you have a basic understanding of plus or minus what that means. Yeah. And it can be derived from any number of places. You can do a calculation, or you can do a measurements, multiple measurements, and just lay in. And typically what you want is some type of expression of where's your uncertainty, right? Are you certain within 95% of that value? Right? 5% error. That's generally where you start. And if your data is really good, sometimes you can claim 1%. Right? But in my line of work, as in agriculture, I was lucky to get 5%. Okay, so the answer is C. It's precise, but not accurate. Now we've got these three. Instead of darks this time, we've got, looks like bullet holes, maybe. Which of the following figures represents a result having high precision? So which ones are grouped close together? 2 and 3, right? Okay. Next question is referring to those same ones. Which of the following concerns? Figure 1 represents a systematic error. Okay, we're juxtaposing systematic versus random error. Okay, we didn't talk about that in class. This is number 13. Systematic versus random error. Systematic error is the type of error where you can identify maybe not what's causing it, but it happens the same way every time. Right? And if it happens, if the error is the same amount every time, maybe in percentage value, but if it's off to this side every time, then all you have to do is adjust your instrument or adjust your calculations to bring it back down. That's the easiest kind of error to deal with, systematic. We know what the error is and we can correct for it. It's like zeroing in your scope before you go out and shoot Bambi. I've seen a bunch of Bambis in the past month, right? They've been in my yard. They've been in the neighbor's yard. I saw 3 of them on the way here this morning.
There's a ton on the other side of the 4 lane.
Yeah. And one of them had, let's see, in this state, how do we count? We count spikes on both. Okay, so this one probably had 6 spikes, but it was small. So where was I going with this? Oh, zeroing your scope. So if you get a bullseye and you're like this, right, with your shots, then this is a systematic error. You can bring it down. You just dope your scope. We know that it's always going to be this way, and we can bring it down to the bullseye. So that means that we're looking for high precision in order for for there to be systematic error. So number 2 and number 3 would be systematic. Right? Let's see. 1 and 2. No. C and D and E just don't work, right? Because 1 and 2 are different, right? 1 is random error, right? It's just all over the place. There's no way to predict it. Now you can compensate somewhat with statistics. But it's got to be A or B, right? 1 is systematic error. No, it's random. So B would be the best. 1 is random error. 2 is systematic error. Now 3 is systematic. Well, 3 is, yeah, there's always error there, but there's not a lot of correction you can do to 3 because it's grouped right around the bullseye. So yeah, they're right. 1 is random error, 2 is systematic.
So
Is B, yeah. Okay, 16 and 17.
when we're studying, we probably study all of it, but we need to key in on the one we're doing right now.
Well, if you understand, right, if you understand how to work these problems that we're covering,
Yeah.
then these cover all the types of problems that you would see elsewhere in the document. I have lots of repetition in there so that you can confidently attack what looks like a different problem, but once you get into it, you realize I've done one of these before. That type of thing. So I've just picked out the ones that are not repetitive. The amount of uncertainty in a measured quantity is determined by what? Well, we didn't specifically discuss this, but very few measurements, at least on the surface of the Earth, very few measurements are made by automated systems. I mean, it's becoming more and more common, but even then, those automated systems are programmed and built by humans. So you still got the human introduction of problems. If you've got a robotic system, say land on Mars, and it starts to sample, then most of the problems there would be mechanical with the system itself. Right? So the measuring device is one place where you have error, and the measurer, the person or thing yielding the device, is also introduces error. For instance, if you want to read the volume in a cylinder, you got markings on it, and you got it. You got the level of say water to that point, then and there are little markings in here too. Let's be kind to ourselves. You want to have your eye level with the water, and the way that you do that with our glassware is periodically the scoring goes all the way around, both sides, and that's so that if you see two lines, if you're looking through that line, you see two lines, you know that your eye is not level. Right? If it's level, you only see one line. And the reason we do that is to avoid what's called parallax error. If you were looking this way, then you might be reading a line that's higher volume than is actually in the device. Or if you're looking this way, you might be looking at it and seeing values on your device that are below the actual volume. That introduces parallax error. So you've got both the instrument, which has limited reproducibility or limited precision and accuracy, and you've got the person using it that may introduce error also. Oh, so the answer is A. Both the skill of the observer and the limitations of the instrument are determine the uncertainty of your measured quantity. Okay, now we're going to use our rules for significant figures and round this number off. Let's see, 17. Like this, 17. So we've got 0.00. No, just 1 0. 1 0. And then 4, 5, 0 0, 6 7, 7 0 0. Okay. We're going to round this off to, before we get started, to round it off to 4 figures, you got to find out which ones are significant. These two right here are not significant. So we have to start counting from here. 1, 2, 3, 4. We want to round off to this position right here. Okay. So if we're going to round to here, we got to look immediately to the right. That one's greater than 5. So this one becomes 0, 4, 5, 0, 1. Okay. Now, all of these are significant, but we have to throw them out if we're going to round to 4. But we don't look over here to round. We look immediately to the right of that position. And that's what determines the rounding. We don't care what else is out here. It doesn't matter. We only care about that one to round this position. So the answer is E.
Any number, if it's 0.0 something, the first two are always not.
Right. Leading zeros are never significant. Yeah. Captive zeros, those that are inside non-zero, those are significant. And right-hand zeros are only significant if there's an explicit decimal somewhere in the number.
So those are there zeros at the end?
Yeah, those are significant. Yep. Let's see. Where's my next highlight? Here's a highlight, 2 highlights. So we'll do those 2. 20. Express the number 0.0810 in scientific notation. 0.0810. Scientific notation means that the coefficient has to be between 1 and 10. So in order to get there, we've got to move that decimal over here and put it right there. If we put it here, it's too small. If we put it over here, it's too big. So we put it right there. And that would be significant, significant, significant. We keep these parts of the number. Now, what is going to be the power of 10? Well, we moved it to the right. We're storing up smaller amounts, right? So it's going to be a negative power of 10. And that's -2. And then check yourself, look at it. What? Is this a small number? Yeah, tell them that's a small number. Is this? That's a small number. Right. So I've had students put a +2 in there and just go with it, not realizing that you just made a big number out of a small number. Okay, that was 20. 21 is go the other direction. We're going to take 6.49 times 10 to the -3 and turn it into standard notation. So what you have to do here is say, which way are you going to move? Well, you got to make a smaller number out of that coefficient. So 6.49, and then I give myself some zeros out here for moving the decimal. Move it 3 places. 1, 2, 3. So we put a decimal right there. We throw that other one away. 0.00649. This had 3 significant figures, and this has 3 significant figures. 0069. A, yes. A. 22. Express this one in common decimal form, which is another way, standard notation. And this one, 22, our number is big. Yep. Okay. Yeah. You just have to find which one is best.
That fits it.
You would move if we were doing 165,000
Uh,
in exponential. Your authors, the authors of the book, and actually the authors of my book from which this was derived, right? I'm using one textbook and you're using a different one. We would move the imaginary decimal point 1, 2, 3, 4, 5 places. And this would be 1.65. And those zeros are not significant.
So it's the same rule, even though it's called something.
Mm-hmm.
Okay, that's what I was thinking. The 930, all those.
Yeah. Okay, so in this case, exponential notation, their concept is the same as scientific. But we could conceivably say 16.5 times 10 to the fourth would be exponential. It just wouldn't be scientific. Okay, this one we want to convert to standard notation. So which way is the decimal going to move? We need to end up with a big number because that's 10 to the fourth. That means the decimal moves to the right. So 2, 3, 7, 0, 0, 0, 0. Just give ourselves plenty of zeros. We're going to move 1, 2, 3, 4 right here. But that's only 3 significant figures. We have to get rid of that decimal so that we only have 1, 2, 3 significant figures. That's the trick to this. Let's see. That was 22. Let me get back down there. Yep, D. 23,700. Okay. Yeah. I like to reason things out, but if it helps, just memorize which way to go. Okay, 23. We generally report a measurement by recording all of the certain digits plus how many uncertain digits? 1, yeah, right. Everything's certain except for the last one to the right. That's uncertain. So B's the answer. Let's just check if you're listening. 24. Okay. You're asked to determine the perimeter of the cover of your textbook. Okay. And it helps to draw a picture for me. Textbook is something like this, maybe. And it says you measure the length is 39.36 centimeters. Okay. And the width as 24.83. Doesn't look like that's the scale. And how many significant figures should you report for the perimeter? The perimeter would be add this, plus that again, plus this again. That's the perimeter, right? So we would have 39.36, 39.36, 24.83, and 24.83 centimeters. We would add those together, and the question is, how many significant figures? We're starting off with 4, but this is an addition problem. It's a different set of rules. You line up the decimal points, and then uncertain, 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 we can keep that last one. So that's 12 plus, let's see, well, 3 times 6 is 18. That's 1. And then we have 16, 17, 23. Right? And that's 18, 19, 20, 28. And that's 6 plus 6 is 12. Correct? So if we can keep this last one, that means we've got 5 significant figures in the answer. So the answer to that one is E. I've had students apply the multiply divide rule to this type of operation and say, oh, the answer has to have 4. Oh, sorry. Have to sacrifice your firstborn. 25. Okay. Consider the numbers 23.68 and 4.12. 2368 and 4.12. What are we going to do to them? The sum of these numbers has how many significant figures? And the product has how many? Okay. So we're going to do it two ways. We're going to add them together first. So that's, we line up our decimals. 10, 1, that's 8. And that's 7 and 2. Right? So we have 4 significant figures by addition. So the answer is either B or D. If we multiply them, though, we only have 3 significant figures. Right? If we change that sign to multiply, then we get 3 significant figures in the answer. So it's 4 and 3, which is D.
So it's 0.80, but 0 is on the right, so it's significant, right?
0.80?
On the, it's 27.80.
Oh, yeah.
So that one's
Right, because this is uncertain, that's uncertain. These are the last ones. Line them up. You get to keep that last one. Yeah. Let's see. 27. Using the rules of significant figures, calculate the following. Right, now this is a subtraction. 2, 1, and 0.179. Okay. First, we line up our decimals, then we subtract it, keeping all our information, and then we decide how far we can, how far to the right we can go legally. So 0 from 1 is 1, 9 from 12 is 3, 7 from 9 is 2, and 1 from 9 is 8, and we have 3 left over, correct? Let's see if that's right. 1, 12, 10, 1, 9, 10, 1, yeah. Okay. So we have to round it to here because that's uncertain and this is uncertain. This one limits the certainty of the number. So we're going to round it off 3.823. That gives us 4 significant figures. And the 1 just drops off because it's less than 5. A. A is the answer to that one. All right. No. What I'm saying is, this is uncertain here. This is uncertain here. The left hand, the most left hand uncertain one determines the position that you can save. Yeah, that's why I drew this line here. So that one drops out because this one determines the right, the number of figures you keep in the answer. Okay, 32. Oh, we got a compound. Let's see how we deal with this one. 3.478 times 1.164 divided by 2.00 milliliters, and this is grams. Okay, minus 0.169 is grams per milliliter. So the units match up because this is grams divided by milliliters, this is grams divided by milliliters. But what we need to do is determine the order of operation. Parentheses come first. So we do this one first. And then you do exponent, we don't have one, multiply or divide. So we do that one first, then this one, divide that into it, and then subtract. Okay. So I'm not going to try to do that with my head. 3.478 times 1.164 So this value is 4.048392, according to my calculator. But 1, 2, 3, 4, 1, 2, 3, 4. We can only keep, well, actually, we can keep all of them. And this is where I mentioned it before, but I'll say it again. When you've got nothing but multiply, divide, you can keep all those decimal points until you get finished with your multiply, divide operations and then round. Because if you do that, then you avoid rounding error. Oh, it doesn't. Let me see. Is yours that way too? Oh. Okay. Let me think about this. Parentheses, exponent. It still works. Right. Multiply, divide first. I think, I don't know why. Maybe I was trying to mess with my students' minds.
So for exam next week, we'll need a calculator.
Oh yeah. Yeah. You need a calculator. You can have scratch paper, and a pencil and eyeglasses if you need them, or contacts. I never have worn contacts. First of all, I didn't like things on my eyeballs. But second of all, I've always been in the sciences from high school on. So from about the 8th grade, I had to wear glasses. So I just wear glasses in the lab, and I've gone that way forever. Anyway, so we got this one. Now we divide by 2.00. And that's 2.024196. 2. Let's say 024. 024196. Did I say? Yeah. Now, this can be limited by, let's see, that's 4, that's 4, that's 3. We want to limit it to 3. Right here. 1, 2, 3. That's a 4, so we keep that one and throw those out. So now what we've got is 2.02 minus 0.169. Right? And we're going to have to limit it right there. So it's, but we do our subtraction first. 9 from 0 is 1. 6 from 11 is 5. 1 from 9 is 8. And 0 from 1 is 1. And we eliminate that 1, 1.85 grams per milliliter. So C is the answer to this one, with or without the parentheses. This must be, I must have a really old key, and your version is newer, and I decided to leave the parentheses out. All right. 37. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. Now, I didn't ask you guys if there were any in here that were really giving you trouble that you wanted to get to do.
Did you call out first?
Yes. Oh, I skipped over it, didn't I? Okay, sorry. Yeah. 35. Express the volume 781.2, 781.2 cubic centimeters as liters. So we want to end up with liters. All right. What do we know about cubic centimeters? Yeah, exactly equal to milliliters. Right. So we can convert this to milliliters. And now we only need one factor. What's the relationship between milliliters? That's still in the numerator. This is in the denominator. So we have 1,000 milliliters per liter, or 10 to the minus 3 liters per milliliter. Either way, we're going to divide that by 1,000. And if you divide something by 1,000, you move the decimal to the left, right? You're making it smaller. So we're going to move it 3 places. 0.7812 liters. D. Did I lose you? Or the other way to do it is say dividing by 1,000 is the same as multiplying by 1,000. So you could move this into the numerator and say 10 to the minus 3.
Okay, that's what I was.
Yeah, that works.
I saw the positive figure, like, why are we not moving it to the other direction?
Because it's in the denominator. Yeah. 35. Now I can do 37. So we're starting with 14.7 pounds per square inch. That's a measure of pressure. What's the pressure expressed in grams per square meter? I should start over here. This is going to be a chain conversion. Per square inch. There we go. We want to end up with grams per square meter. Okay. When you have a compound unit of measure for your starting position, convert one at a time. Right? And you don't have to do separate. You don't have to convert this and get a number and then convert the other one. You can do it all at once because we're only multiplying and dividing across here. So you can just chain them all together. Right? Convert pounds. Right? Pounds is in the English system and grams is the metric system. So we need something to bridge the gap between the two. And what we've got there is pounds per kilogram. Pounds equals 1 kilogram. Okay. But we get it into the metric system, then we can convert the kilograms to grams. So we want to get rid of pounds. They're in the bottom, kilograms in the top, and then we plug in the numbers. 2.205 pounds. 2.205 pounds per kilogram. There we go. So pounds cancels out. Now we got kilograms. And we want to go from kilograms to grams. All right, so 1 kilogram is 1,000 grams. Okay. So now we got grams there and here. Kilograms. There we go. Now we want to convert square inches into square meters. We're doing them now. We want to convert inches into the metric system. So we got inches. We know the relationship between inches and centimeters is given there, 2.54 centimeters. And the metric unit is in the denominator, so that's where it should be. Right, 1 inch. The problem is they're squared. That's squared and this is squared, but that's not squared. So here's the solution. Square the whole thing. That'll square both the unit and the value. Okay. So this squaring that inches cancels it. And then we need to square, we'll get the square centimeters, and then 2.54 has to be squared also. Okay. So that gives centimeters. Now we want to convert to meters. So centimeters and meters, we know that there are 100 centimeters in a meter, right? Because a centimeter is a hundredth of a meter. So we need 100 centimeters to make a meter. Okay, but we still have a square problem. This is going to be squared by that. So now we need to square this one. And that gives us a square meters here. That gives us square centimeters there. That cancels this square centimeters. And that's the thinking part. The rest is number crunching. So let's see if I did it right. So with your calculator, I just say multiply across here and then go back and divide across here. Oh, step by step. That's all you have to do. You don't have to keep intermediate values. 1,4.7 times 1,000 times 1. 1 squared is 1. Let's see. I won't start that over again. I'm afraid I hit the wrong key. Okay, 1. This is 10 squared. 10 squared is 10 to the 4th, right? When you square an exponent, you multiply the two exponents. Right? So that would be 10,000 times. Then we'll go back, divide by 2.205. Yeah. Okay. What did I do?
The 10. Why is the 10 squared eating? Why is that?
So that we can square the unit.
Why is the 10? Why is it 10 squared?
Oh, because they're 100 centimeters in a meter.
Okay.
And 2.205 divided into that, and 2.54 squared first, and then divided into it. Right? And I get 1.03. Let's see. These are exact numbers because they're conversion factors. So you only have to consider this one, 3 significant figures, because it's all multiply, divide. So 3 significant figures, it's 1.033333. So rounded off 1.03 times 10 to the 7th grams per square meter. Let's see, what did I do wrong? I didn't do it. I didn't. Oh, I got it right. B. I've been known to get them wrong. What's the question?
You only consider those for the significant figures, like how many-
Yes. Right. These conversion factors are considered exact numbers.
Okay.
They have unlimited significant figures. Now, if we had 2 measured values multiplied together, you'd have to consider the 2 of them and which one is the smallest number of significant figures. But since we've only got 1 and we're converting it to something else, then this is the only one that determines the answer.
So if you get 10 to the 7th, feel like how many threes there were? And I guess since how we do.
Well, I've got my calculator set up to spit the answer out in significant. Yeah. Yeah. And you should be able to set yours up that way too. Unless you're using your phone, and that may not be that friendly. Do you have a scientific calculator?
I think I have one at the house.
Okay.
I didn't leave my phone.
Check the battery.
I don't have. That's why.
Now, during the test, you got to have one. Does it say scientific on it? Let me see. If it doesn't say scientific, you just need to check the functions.
Yeah, I have that. I still listen to my husband. Yeah, I have it in my husband too.
Got all the 3 functions. Got squares, square roots. Got reciprocal key. Logs. Got both common log and natural log. Yeah, that's got everything. It's a solar calculator. You don't need a battery. You just need light. How are we doing on time? Okay. All right, 41. The density of liquid mercury is 13.6 grams per milliliter. What's its density in pounds per square inch? This one is similar to the one we just did, only it's going this time from metric to standard, or metric to English. Or sometimes they say metric to imperial system. Same thing. 13.6 grams per milliliter. And we want to convert that to pounds per cubic inch. Okay, so let's convert grams to pounds. We know that the relationship between English and metric is 2.205 pounds per kilogram. So this needs to be converted to kilograms before we can use that measure. Right. Grams in the bottom, so they'll cancel. 1 kilogram is 1,000 grams. Right? Okay, so now we can use the conversion for kilograms. 1 kilogram equals 2.205 pounds. It gets rid of kilograms. Now we got pounds covered, right? We're good. Now we want to do volume, milliliters to cubic inches. So in order to do this one, we know the relationship between inches is in terms of centimeters. So we just need to convert milliliters to, and we can put the step in here. 1 milliliter equals 1 cubic centimeter. Okay. Now we can convert centimeters to inches. Let's see. 2.54 centimeters for 1 inch. But in order to cancel this one out and leave us cubic inches, we need to cube that ratio. Okay. Is that messing with your head when I do that?
It messes with me because you leave the pounds behind, like I don't understand why the pounds.
Oh, the pounds?
I know that's the.
You have
Right here.
to take down pounds because you have to do the
I know that,
one to get the other.
Okay.
but now you're trying to cancel out the kilograms,
Right.
so why?
First we worked on the top to get pounds, and now we're working on the bottom to get cubic inches. So I couldn't, there's no way to get milliliters from metric to English system. So I had to use the equivalent of milliliters to cubic centimeters.
That's what-
Okay. Yeah, I forgot to cancel that one and that one. And now I need to get cubic centimeters. This is the linear ratio of centimeters to inches. And this makes it the volume ratio of cubic centimeters to cubic inches. I'm also going to cube that value. Well, if we cube this whole thing, what does that actually mean? It means I could do it this way.
I was gonna deposit it on sale, but I think I understand what you're doing. Process it.
See, works the same way. Instead of writing it out like that, I just put a 3 here. And it cubes it. But this way you get centimeters times centimeters times centimeters is cubic centimeters, right? And you multiply that times that times that, which is cubed. And this is 1 inch times 1 inch times 1 inch, which gives you cubic inches. And 1 times 1 times 1 is 1 cubed. Yeah, right.
Yeah, I did that.
Okay. So that's the thinking part. So if you multiply all those out, it should come out to 4.91 times 10 to the minus 1 pounds per
Aren't the inches
cubic inch.
big?
Yep. No, inches are cubed.
Yeah, yeah. So that's the conversion. Oh, inches are supposed to be 15 meters, so that's.
Yeah. Let's see. Here we go. 46. They're getting more complicated as we go, deeper and deeper. Next is 46.
Some questions were in there.
I think they're in this one or in the,
Oh, okay.
oh, I don't know how many highlighted ones I've got in here.
Yeah, there's 80 in the first.
During a physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? Well, you need a starting position. Speed of light is 3.00 times 10 to the 8th meters per second. Times 10 to the 8th meters per second. But the electron's not going that fast, right? It's only going 93% of that. So the decimal equivalent of 93% is 0.93, correct? That's our starting position. That's the starting value for the speed of the electron. 3 times 0.93. 93% of this value. Now we want to convert it to miles per hour. So we're going to do meters first. How many meters in a mile? Is that given to us? Meters at miles and kilometers. So let's convert meters to kilometers. Meters to kilometers. How many meters in a kilometer? 1,000. Okay, so we cancel that one. Now we've got kilometers, we can convert that to miles. 1 kilometer is 0.6214 miles. Okay, so the kilometers cancel. Now we got miles. Now we want to convert seconds to hours. So you know how many seconds are in an hour? If you don't, we can chain what we do know together and make it.
60 times 60.
Yeah, 3,600, right? Seconds are in the denominator, so it's 3,600 seconds in 1 hour. Oops. What am I doing? Hour. There we go. So we got rid of the seconds. Now we got hours. That's it. We got miles per hour. And if we do our math right, we should come out 6.2 times 10 to the 8th miles per hour. Now, if we left this part out, what would that give us in our units? Miles per second, right? And everybody knows the speed of light, miles per second, I think. 186,000.
So the, that's just MI, I don't know.
Yeah, that's miles. Okay. You just have to crunch the numbers and get that answer. I don't want to eat up all our time doing this and not have any time for the lab. That's why I'm not doing the calculations anymore. 49, unless it's called for. You know, I may do one. In 1928, 29.3 grams of a new element was isolated from 660 kilograms of the ore molybdenite. The percent by mass of this element in the ore was. Okay, it's probably molybdenum was the element. I mean, just guessing. But how do we do percent by mass? We do the mass of the element divided by the total mass of the ore, correct? Times 100. But there's a fly in the ointment here. There's 2 different units of measure. Kilograms and grams. So our percentage is going to be 29.3 grams of the element divided by how much ore? 660 kilograms is how many grams? 660 kilograms. Right? If we write kilograms, what does kilo mean? Kilo means 1,000. So let's substitute 1,000 here. And that's how many grams. Okay? Times 100, and that'll give us percent. So it's 660,000 divided into 29.3. I can do this one. So after I multiply times 100, I get two significant figures, right? This doesn't have a decimal, so there's only two significant figures. And if I round off the answer my calculator gave me, it's 4.4 times 10 to the minus 3. 4.4 times 10 to the minus 3%. But our answer is probably it's in standard notation. So let's do this, 4.4, then we're gonna have to move the decimal to the left. 1, 2, 3. So it's 0.0044%.
You multiply it by 100 to change it to a percent.
Yes, yes. Yeah, percent is a tricky unit of measure because there's no dimensions. Right? In this case, we divided grams by grams. Grams cancel. It's just percent just means parts per 100 parts, and that could be mass per mass, it could be mass per volume, it could be volume per volume, it could be atom percent, atoms per however many atoms, 100 atoms. Right? So percent is really tricky, and you need to insist, if anybody's going to give you an answer in percent, that they explain what they mean by that. Okay. Temperature conversion. 409 Kelvin. 409 Kelvin is what? Well, we've got centigrade and Fahrenheit. So you know that we don't have a formula that'll convert directly from Kelvin to Fahrenheit. We could probably invent one, but for our purposes, we would convert Kelvin to Celsius first and then convert Celsius to Fahrenheit. So we're going to have to go through Celsius anyway. Let's do that calculation and see if either one of those, D or E, matches up. Right. So what's the value? 273. Right. Yeah, because K equals C plus 273. So C would be K minus 273. Yes. Oh, yeah. Yeah. It's just a formula. So let's see. That's 3 from 9 is 6. 7 from 10 is 3, and 1. 136. Yeah, 136 degrees Celsius. And that's D. We don't even have to convert it to Fahrenheit. We found the answer. Okay. Uh, 51. Melting point of a certain element is 391 C. What is that in Fahrenheit? Okay, this one we do have to use the formula for the conversion of Celsius to Fahrenheit. So we got 391 degrees C, and we want Fahrenheit. So remember the formula? Fahrenheit equals 9/5 C plus 32. Or your textbook might say 1.8. It's the same thing. 9 divided by 5 is 1.8. So we want Fahrenheit. This is the way it should be then. We just plug in 391 right here times 9/5 plus 32, and we should get 736 Fahrenheit. Okay? Just memorize the formula. All right. 54. All right, 1984, some drums of uranium hexafluoride were lost in the English Channel. So, uranium hexafluoride. Hexa is 6. So, uranium hexafluoride were in drums that were lost in the English Channel. The water in the English Channel is 17 degrees at the bottom. 17 degrees Celsius. Okay. The melting point of uranium hexafluoride is 148 F. So the melting point is 148 degrees Fahrenheit. Okay. So, and what's the physical state of uranium? Is this temperature warm enough to exceed that value? Probably not. Right? If you're in a hurry, you're probably right. But either we convert this to C, compare it to that, or convert this to F and compare it to that. So it's probably simplest just to Fahrenheit equals 9/5 17 plus 32, which would be about 63. Two significant figures. 63 degrees Fahrenheit. So the water is too cold. It's not warm enough to melt it. So the uranium hexafluoride is going to be in the solid form. Okay. So why would anybody want to make uranium hexafluoride? Any idea? Well, you know, uranium, got a question? I see wrinkled brow.
Well, you ever ask the question that says not enough information? You ever like want to change? Give us.
Oh, sometimes, yeah.
So if it was hot enough, then it would be in a liquid.
Yeah. Mm-hmm.
But how do I know about gas? Water.
Oh, yeah. You can't tell it from that.
So if it asks us, you have to say on it.
Right. If you determine the temperature, well, actually, if you determine the temperature to be greater than 148 Fahrenheit, then it could be liquid or it could be gas. Right. So in that case, you could probably argue for E. Right. You're not giving enough information. You need the boiling point too. That's a good point. Yeah, uranium hexafluoride.
That's why I was wrinkling my eyebrow.
Okay. Yeah, no, that's a valid concern. If I'm expecting A, but say I change the parameters so that the temperature of the water is high enough so that it's above 148. Now, is it a liquid or is it a gas? We don't know because you don't know the boiling point. Right? In that case, you would have to say E. But in this case, we know that it's too cold.
Since we know it's not hot enough to be a liquid or gas. And it has to be
Right, right.
okay.
I dodged that bullet. Okay, 56. A monolayer. What's a monolayer? It's got one layer, and in this case, it's one molecule thick. That's what it means, monolayer. Of oleic acid. That many grams, 3.23 times 10 to the minus 6 grams, has an area of 20.0 square centimeters. Okay, so if I've got if I'm looking down on a container of water and I drop oleic acid into it, what's it going to do? It's going to separate into individual molecules, but oleic acid is a fatty acid, so it's got it's got an acidic end on it, like that, carboxylic acid, and then it's got this chain, this carbon chain. what that does is it makes this hydrophilic, likes water, and this doesn't like water. So what it does is it stands up on its head, stands up on the head with its tail in the air. Because this likes water and this doesn't, so this is going to be away from the water. That's why we know that the length of the molecule is the depth of that monolayer. Okay? That's a lot to process, I know. So how do we measure the area or the diameter so that we calculate the area? Well, you dust the water with talcum powder. Right? And then when we drop the oleic acid on it, it goes, right? It shows you the outline. Okay? So we've got this 20 square centimeter area, and we've got a mass of 3.23 times 10 to the minus 6 grams of oleic acid. And the density of oleic acid is 0.895. Density equals 0.895 grams per milliliter, or cubic centimeters, either one. The question is, what's the thickness of the monolayer, or the length of the molecule? So if you turn this on its side, what you're going to have is a cylinder. And this is the molecule is crosses that depth of the cylinder. So what's the volume of a cylinder? You remember that? It was height times area. So the height of the cylinder times the area is the volume. So far, so good? All right. What are we trying to get at? The question is, what's the thickness of the monolayer? What is this height right there? So we know what the area is. We need to find out what the height is. So we need to, we need to find out the, we know the area, we need to find the height, but we don't know the volume. So how do we find the volume? Well, we go back to density, right? Density is mass per unit volume. Right? So we know the mass right here. If we plug in the mass right there, we know the density, we can solve for the volume. Now the volume goes right in here. We know that value, we solve for the height. Did I lose you?
No, we know the mass.
Let me draw that again. We know
We know the density.
right. If we're going to find the height here, then we need to use the volume of the cylinder. Okay. So we know the area because it's given to us right here. The height is what we're looking for. What we need is to find some way to get the volume out of this. Right? We know the density of oleic acid. So if the density is this, and we know the mass, then we can find the volume, and then the volume goes in here, we can solve for the height. Okay?
So when it's grams, it's always mass.
Yeah, grams is mass. Yeah. So if we plug this grams into here, right there, and that's equal to this value, how do we solve for volume? All right, let's do it this way. Density equals 0.895 grams per milliliter is equal to mass, or 3.23 times 10 to the minus 6 grams divided by volume. So volume would go over here, density would come over here. So we divide this value by that value. 3.23 exponent minus 6 and divide by 0.895. So that's 3.6089 times 10 to the minus 6th That's milliliters. Milliliters. Okay, so there's your volume. Now we plug the volume in here. Right? 3.608 times 10 to the minus 6 cubic centimeters. Let's do that instead of milliliters. Cubic centimeters works better because the height is going to be in centimeters. The area is in 20. It's equal to H times 20 square centimeters. That way, 2 of these centimeters cancels and leaves us with 1.
How did you,
Yeah, go ahead.
how did you get the volume in just real fast? I understand, I know the formula, but I don't understand about that.
I moved, I solved for the volume.
Yeah.
The volume in this arrangement is in the denominator, but it needs to be over here by itself.
Yeah.
So I put it over here and I put that over here.
You might have nothing all night.
Huh?
You made the 0.895.
Yeah.
Denominator.
This right here is equal to mass divided by density.
Oh, okay.
Okay.
Okay, that's right.
So mass and density go there, and that gives us this value. So now I put the volume over here, and there's the height, and there's the area. I need to solve for this one. So this is going to be volume divided by area. 3.6089 times 10 to the minus 6 cubic centimeters divided by 20 square centimeters. And that'll leave us with centimeters. So the height or the length of the oleic acid molecule is 1.8. Let's see, 3 significant figures. I'm going to go ahead and round it off. Times 10 to the minus 7 centimeters. Okay. This is one of those types of problems you can't solve it in one step. Complicated problems often have to be broken down into simpler steps. What you need is to say, where are you headed? We're headed to H, height. And that's relative to this cylinder. When you think of it in those terms, think on the microscopic level, the length of that molecule represents the height of the cylinder. And we know height, we've given area, so times the height would be the volume. That's the link. Once you know that you need volume to solve, then you can go back here and get the volume.
So height can also equal volume divided by area.
Yes. Yeah, that's what we did. I solved for this one by dividing both sides by this. So that puts this and that in the denominator and height's on one side. Yep. Let's see. Be sure I'm not eating up all our time. Okay, we got till 5. All right, that was 56, 57. 57's easy. It looks complicated, but it's not. And I'll explain. There, 57. The density of gasoline is 0.7025 grams per milliliter. Grams per milliliter. At 20 degrees, when gasoline is added to water, what happens to it? Well, if you look at the answers, it's asking us, does it float or does it sink? Or does it mix? Yeah, it floats. Why? Because the density of water is 1 gram per milliliter. Anything less dense than water will float, as long as it doesn't dissolve in water. Right? Does gasoline dissolve in water? No. Now, gasoline is a hydrocarbon. It's hydrophobic. so it won't dissolve in water. It's kind of like mixing your own salad dressing, mixing oil and vinegar together. Right? If you just put them in the same jar, you see two distinct layers. So if you're going to put it on your salad, you got to add a little spice to it, and then shake it like crazy to break up all the globules of fat until you get them on your salad. Now, why would we want to do that? Because a lot of the interesting molecules, the flavor molecules in food, are fat soluble. Right? But the vinegar gives it a little bite, so you get both. The oil will extract some interesting flavors from the spice, and so will the acid. There's two different types, so you get a combination whammy when you put that salad in your mouth.
They will float to the top.
Yes, it'll float, right? Because the density is less than water. Anything that's less dense than water will float. What rock will float in water? There's one. No? Yeah, real porous. It's pumice. It's a volcanic rock. What happens when it gets blown out of a volcano? There's so much gas with it. The gas mixes with the pumice, and actually gas dissolved inside the lava starts to expand when the pressure's let off, and it like that. But it cools fast enough where it traps the air inside, and the bulk density of that piece of rock is less than water. Now the mineral density, right? The minerals that of which it's composed, much denser than rock. Like let's see, scratch my head, about 3.5 times the density of water. But if you mix in all that gas, then you decrease the overall density of that rock to the point that it'll float. Okay. A piece of zinc with a mass of 12.14 grams is submerged in 46.3 cubic centimeters of water in a graduated cylinder. All right. Yay. The water level increases to 48 cubic centimeters after you add the zinc to it. The correct value for the density of zinc is what? Right, we're looking for density. So we know we have to solve this equation, mass per unit volume. Do we have the information we need? Well, yeah, we have the mass, right? 12.14 grams. How do we find the volume? Right, draw a picture. Graduated cylinder. We start off at 46.3 cubic centimeters or milliliters, same thing. When we put the zinc in it, it's a regular shape, say. The volume of the water increases to 48. Okay. What's the volume of the zinc? The difference between the two, isn't it? Right? Volume by displacement. This works as long as the object doesn't react with water. Zinc won't react with water. Other metals like copper, iron in the short term. But if we try to put sodium in there, a chunk of sodium or a chunk of potassium in there, or a chunk of calcium, metal, it wouldn't work because they'll react with the water. So it has to be non-reactive. But the volume now is 48 minus 46.3. Cubic centimeters. So this divided by the difference of those two. And in this case, you do want to do this one first. Right? Order of operation. Put the parentheses around here. Do this one first, then divide it into that. And you should get 7.1 grams per cubic centimeter. Okay? All right. The boiling of water is what? Are we still in chapter 1? Okay. Uh, 62. The boiling of water is what? A physical or a chemical change, first of all? It's physical. You're just changing the phase from liquid to gas. Right? How do we know that it's only a physical change? Because it can go back, right? The water did not change. It still is identified as water. So which one works for that? Well, A and B are both physical. Water merely disappears? I don't think so. Gaseous water is chemically the same as the liquid. That's the one. Right. Got a bunch of duplicates. Okay, here. 70 to 73 references these pictures. Right. So A, B, C, D, E. Let's see. Let's put them over here. A, B, C, D, and E. I wanted to talk about this one because if you don't understand what's meant by those little figures in there, then it may be difficult to interpret the questions and get the right answer. So A looks like it's composed. Each one of these symbols is an atom. Okay, so it represents an element. So what do we have in the first one? The first one we have a clear circle, we have a grayed out circle, and we have a diamond. So we've got 3 different elements in there. Right? It's a mixture. But what type of mixture is it? Well, the clue there is the distance between the atoms. The distance between the atoms implies that since none of them touch each other, that it's probably a gas. So the first one is a gas, and it's a mixture of 3 elements. Right? That means it's a homogeneous mixture. All gases, all gas mixtures are homogeneous. They are, in effect, solutions. There are no exceptions. You put 2 or more gases together, you always get a homogeneous mixture. B, on the other hand, everything is locked together and it looks like they're arranged regularly. That's a solid. And it's a solid of 1 element because we only have the gray circle. That's it. Okay. How about C? We have molecules in there. We've got a small gray atom linked to a large clear circle atom. So that's a compound, but it's not a mixture. It's a pure substance. It's a pure compound that's in gaseous state because they're separate from one another. Look how far apart they are. Right, so C is a gas, but it's a compound and it's pure. There's only one type of compound in there. Okay. How about D? Well, let's see. It's not regularly arranged. So what we've probably got is a mixture that's a liquid. Right? Because they're touching each other. But they're not regularly arranged. And there are 2 different elements in there. Right? So it's a mixture. Probably a liquid. Because there's no regularity to it. And it looks like it's heterogeneous. Unless the answers prove me wrong. That's possible. The last one. So it looks like we have elements and compounds in this mixture, and they're regularly arranged. So this one is homogeneous. It's hard to tell if it's supposed to be a gas or something else. Looks like a gas, but it's a homogeneous mixture of element and compound?
Gas?
That would be my first guess. Let's look at the questions. Which best represents a homogeneous mixture of an element and a compound? Well, yeah. It doesn't ask us if it's a gas, or it just says, is it homogeneous and is it element compound? So E works best for that.
What do you mean by
Well, look at it. It's got
that? Oh, where,
This-
where it's got something on it.
Compound.
it's got that one and it's got that one.
And
That's an element, that's compound.
tonal genes are very much the same.
Yeah.
They're regularly arranged. C, which best represents a gaseous compound? Right? So it can't be A because that's a mixture. So a gaseous compound would be C. Okay. Which represents a solid element? Well, that would have to be B. Right? And which represents a heterogeneous mixture of two elements? I think D, don't you? Yeah. Is okay, 70. All right, we're on to something new with 75. Sometimes it's hard to interpret the pictures that they draw. That's why I want to throw that one in there.
I think in high school, we covered all this, like the first semester. And we're doing it in my one class.
Oh yeah. Things move a lot slower in high school. Yeah, I've got a dual enrollment class from New River. They're at Mercer campus, the high school down there, which I forget the name of it. But I've got 17 of them in that class tackling essentially this class and the lab. And we had a Zoom meeting yesterday, so I kind of orient them to the college experience. And they were very quiet. And the proctor in the background says, they're not usually this quiet. So they were like deer caught in the headlights. We'll see. All right. Which of the following has a different value on the moon compared to Earth? All right. Time, moles. Moles is numbers of things. Weight or mass? Mass would be the same. So weight would be different. Yep. Weight would be different. Moles is a way of counting numbers of things. No, time wouldn't change. In Newtonian physics, time doesn't change. In relativistic physics, yeah, it does. Right? When you get close to a black hole or you accelerate close to the speed of light, then time starts to change. According to Einstein. 80. Which separation technique is based on difference in the volatility of the substance to be separated? So what you're doing is you're essentially boiling the mixture, and the more volatile substances come off first. I'm sorry? Yes, distillation. Every moonshiner knows it. Right? They know that when you start to boil your mash, the first thing that comes off is wood alcohol, methanol. You throw that away. Huh? Yes, it will make you go blind if it doesn't anything else. So they know for the safety of their customers to throw that first bit off. And you can tell the difference by smelling them. Ethanol smells a whole lot different than methanol. Ethanol? Yeah, they put that in gasoline. I think up to 10% in most gas stations. Yeah. It's called, well, it's derived from corn. Right. The sad part about that is it takes more energy to produce a gallon of ethanol than the energy you get back when you burn it. Which means, from a business standpoint, that the ethanol business that supplies ethanol to the gas companies wouldn't be there if it weren't for government subsidies. If they had to make it on their own, they'd go bust. Distillation, yeah. What about filtration? While we're here on the subject, yeah. What is the basis upon which filtration works? Yeah, it's a mixture, right? And you can filter one from the other if the material through which you filter has a small enough pore size. Yeah, it's based upon particle size. Volatility. That means at what temperature does the substance boil? So if you have a mixture, two or three, for argument's sake, 2 or 3 substances in a mixture, say liquids, then as you heat them up, the first one that comes off in the vapor phase is the most volatile. It has the lowest boiling point. Right? And I remember as a student in chemistry class, we had mixtures that we put in a round bottom flask, and we heated it with a heating mantle, and it started boiling. And up here, we had a connection with, let's see, like this, that, and we have a thermometer here. And that thermometer would tell us the temperature of the vapor coming off of it. Okay. Well, the vapor would go over here, and we'd have a condenser with water running through it. Right. And it would cool the vapor and condense it. And it would come out down here and drip into a container. Okay. How do we know when to stop catching one and get ready to catch the second one? Watch the temperature. Once the temperature is going to stay right there until all of the first component's gone. And then when the second one starts to come off, the temperature will rise. And at that point, we'll take this off and put the other one in. And you do that for however many fractions there are. And then you take that purified substance and you go do some other stuff on it to identify the unknown. One thing you can do is put it in an infrared spectrometer if it's an organic compound. The other thing you can do is stick it in a device that determines the refractive index of it. You can stick it in a pycnometer and determine its density. And all these key factors come together and help you identify what it is. And your grade's based upon that. That was the one class I got a C in, because I took a shortcut. The substance that I was given, this was one of the substances. All I had to do was identify it was already pure. So it was multiple types of procedures we had to do. This one procedure, what had happened was it was an aldehyde, and that doesn't mean anything to you now, but aldehydes will oxidize into acids. And when they oxidize to an acid, it turns solid and sits on the bottom. So what I did was I poured it through a filter and I collected the solid and I put it in, pressed it into this little disc and stuck it in the infrared spectrometer and determined what the acid was. And once I knew what the acid was, I could back figure to the aldehyde. And that's what I submitted for my report, and the professor didn't like it. So, because I took a shortcut. Yeah, it was still right. That's all right. That's water under the bridge. It was only a lab course, right? It wasn't worth a lot of credits. But it was fun. It's kind of crowded though. We had graduate students in there doing their organic chemistry, and they would purify their mixtures. They'd do a reaction, and it'd have stuff in there they didn't want and stuff in there they did want. So they'd pass it through these huge columns of aluminum oxide. And they'd use chromatography to separate enough of the compound so that they could do further tests on it. So the columns would be about that big around and about 8 feet tall with aluminum oxide in it. And they'd wash it through there and and it would separate. That's the nature of chromatography. By the way, let's go back. Distillation, paper chromatography. Paper chromatography and all chromatographies are based upon the difference of affinity between the molecule and the stationary phase. The stationary phase is paper. Right? So we got a strip of paper, and originally the extract was of leaves. I forget the guy's name. He was, I think he was Polish. And he extracted leaves, and he took the extract and put them on that paper right there in alcohol, I think, and let them dry.
I did this in biology.
Yeah. And then you submerge it in this device, and you only have enough liquid so it touches the bottom, and you don't let it touch.
It bleeds up.
And then you like that. And as it moves, the mixture in each one of those extracts, some of the molecules have a strong affinity for paper, and they'll lag behind. And the ones that don't attract paper very much, they'll stay in the mobile phase, which is wicking up the paper, and they'll move faster. So eventually you get separated colors. Right. So the key to that separation is differential solution in the mobile phase versus attraction to the stationary phase.
So we need to know that, like, we can go to test if you're after.
I might. Yeah. Yeah. Solvent extraction, I probably won't hit you with that one.
Is that stuff in the
I don't think it's in there. It might be in your book. Solvent extraction is a little more complicated. Best example, I'm going to take off from our salad dressing. If you've got spices in there, in oil and vinegar, they'll extract different compounds. So if you mix them up, then the spice is exposed to both of the components. Then you let them settle, right? They'll separate, and they separate into 2 layers. And this one will have some of those components, and this one will have other components, the acetic acid or the vinegar. And then you just drain off the bottom, and that separates the 2. And you've got a separation between those 2 types of molecules. That's solvent extraction. I used to use this too for, I forget what it was. I was working with crawfish processing waste. Yeah, everybody know what a crawfish is? Okay. You ever eat one? Okay, they're good. But there's only 15% of the weight of the crawfish is tail meat. The rest is thrown away. So when I was working in food science as a master's student, we were trying to figure out, my professor was trying to figure out what could we do with the waste to help the processors, because the EPA was going to come down on them. They couldn't just dump it. So we extracted the red color from the carapace, right, and used that in fish diets. Now, some fish take the carotenoid pigments from their diet and deposit it in their skin. That's why naturally caught salmon is pink. It has pink flesh, because what they eat has the carotenoids in it, and they deposit it in their flesh. So farm-raised salmon is white. It's unattractive meat, right? It doesn't sell very well. So if we put these carotenoids in their diet, then when the farmers feed them that, they'll get pink flesh. And we worked on that, different types of diet formulations, and I had to characterize there's a whole class of compounds called carotenoids derived from carrots. Right? The word is derived from carrots. Right, the orange color in carrots is that type of compound.
That likes your eyes. That's good for your eyes.
Good for your eyes. Right. In World War II, they used to give the pilots carrot pills. Right. It aided in their night vision, but it also turned the yellow part of their eyes kind of orangish. Anyway, so I use solvent extraction to separate the carotenoids from the preparation that I'd made with the shells. And that was one of the cleanup steps, was to do that solvent extraction. And then I did some thin layer chromatography, which is kind of like paper, but it uses a coating of silica gel on a glass plate instead. And quantitatively separated them and identified what each one was. Thin layer is nice because once you get the spots separated and you pull it out, you can scrape off that little circle, that colored circle, and put it in a little vial and extract it, and stick it in your machine and figure out what it is. But paper is a little more difficult. Plus, paper doesn't work very well for separations. Okay, we're into chapter 2 now, and I've only got 2 hours, so I'm going to have to kick it up a little bit. Chapter 2. For any calculations, what I may have to do is just set up the calculation and then let you finish it off to get the right answer. Okay, it looks like the first few questions are just pure memorization. Right. 1. The first people to attempt to explain why chemical changes occur were? Yeah, the ancient Greeks, right? The first chemist to perform truly quantitative experiments was Robert Boyle. Yep, he backed up his laws and his theories with experimentation. 3, the scientist who discovered the law of conservation of mass and also is the father of modern chemistry. Just think beheading. Lavoisier. Lavoisier was a French scientist who also had a contract to collect taxes from the king. The king, Louis XVI, gave him a contract to collect taxes, and you know how that works. You give the king the taxes he wants, and everything else you get to keep yourself. So nobody liked tax collectors back then either. Unfortunately, the French Revolution came around, and Dr. Guillotine produced his infamous device, and a lot of people lost their heads, including Lavoisier, because that they wanted to get rid of their enemies. Yep, sure is. His wife helped him too. I'm not sure if she lost her head or she got away. Of course, Louis XVI and his wife Marie Antoinette they lost their heads. Yeah, Marie Antoinette. She wasn't French. I think she was Austrian. Right. All those royal families in Europe in those days, they intermarried to solidify their treaties. Okay, number 4. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Remember, multiple proportions. Example, if you have nitrogen and oxygen combined, it can do like that, or it can do like this, which is probably an ion. But if you hold this mass constant, then these masses are a ratio of 1, 2, and 3. That's multiple proportions. So in order to satisfy the conditions for that law, the 2 parts of the compound must be the same. And then you have the relative amounts. So A, ammonia and ammonium chloride won't work. B, zinc 4 oxide and zinc 4 chloride, or zinc 2 chloride don't work, right? Because oxygen and chlorine are not the same. H2O, water, and HCl, right? You don't have a pair there. NO and NO2, there you go. You got nitrogen and oxygen together. You've got 1 oxygen in one and 2 in the other. That's multiple proportions. Now, we draw them that way today because we understand that the multiple proportions law based upon mass is due to the ratio of atoms. But when the law was developed by Proust, they didn't know that. That had not been developed as a law. That came along with John Dalton. Okay. A sample of chemical X is found to contain 5 grams of oxygen. So we got, let's see, number 7. 7, it has 5 grams of oxygen, okay, in this compound, has 10 grams of carbon and 20 grams of nitrogen. Yeah. The law of definite proportions says that this ratio in that compound is fixed. Right? It's always 5 to 10 to 20 for that compound. So if we have 70 grams of that compound, how much of carbon will we have? Right, because this is what? That's 35. And if we go to 70, we just doubled the amount, right? So we doubled that amount to 20. Yep. Okay, which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? All right. That's number 9. Well, let's see. Elements are made up of tiny particles called atoms. Yep, that's still true. Atoms are not created or destroyed in chemical reactions. That's also true. All atoms of a given element are identical. Isotopes. They're not identical. They're chemically the same, but they're not identical physically. That's how we separate isotopes, because each atom of a different isotope has a different mass. We can use that to separate them. Well, we found our answer. And in the interest of time, we move on. 11. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of compounds, and for discovering selenium, silicon, thorium is. We didn't talk about this person. Might be in your book, but this was Berzelius. Berzelius was a Swedish chemist, and he proposed a system of representing the elements with symbols, just letter symbols. Dalton had another proposition, and his were they were really harebrained. Different types of shapes and crosses and all that. It was a mess. So I'm glad Berzelius won, because now we have symbols that are either single letters, capital single letters, or capital small, if there are 2 letters, representing the elements. And then if you put them in a compound, then all you need is the subscript, like, I don't know, water. Right? There are 2 hydrogens and 1 oxygen in that molecule. So the subscript here tells us how many there are. And that was Berzelius. That was his idea. He's got a beaker named after him, too. Just like Erlenmeyer's got a flask named after him. I don't know if I'd want to take that to my grave. Number 12. Avogadro. Avogadro's hypothesis says what? Remember? If you have 2 gases in separate containers, and it doesn't matter what the gases are, as long as they're gases, if the volumes are equal and the temperature is equal between the 2, and the pressure inside the container, both are equal, then the number of particles in each one has to be equal. That's Avogadro's hypothesis, which means the best answer is D. All right. Let's see. 13. The first scientist to show that atoms emit any negative particles was. Remember that one?
And that's the student.
No, no, that was J.J. Thomson. He was the one that used the cathode ray tube. Yeah, J.J. Thomson identified the negative particles were coming from matter. So it means that the atom was not just a jelly-filled bag. It had particles in it. Rutherford.
Yeah.
Yeah, the gold foil experiment, Rutherford.
What was the student's name? I think.
The student of Rutherford, it's not there as Chadwick.
Okay.
Yeah, Chadwick identified the neutron.
Negative particle.
Right. 14. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Well, Rutherford's experiment, well, if we say that Rutherford proved the Thomson plum pudding model of the atom was essentially correct, that is false. He actually laid that one to rest with the nuclear model. That's what his experiment showed. So A is the answer. Scientist whose alpha particle scattering experiment, Rutherford, right? He fired alpha particles out of thin gold foil, which was only 3 or 4 atoms thick, and proved the nuclear model. So here we go again. 16, alpha particles beamed at a thin metal foil may what? Pass directly through without changing direction? Yes, that's true. Or be slightly diverted by attraction to electrons? That's true, right? Because the alpha particles are positively charged and you got the negative whatever going through, so it could be deflected.
Alpha particles are always going to.
Yes, alpha particles is in fact, this alpha particle is a helium nucleus with no electrons, right? It's got 2 protons and no electrons, so it's just the nucleus of the atom. The difference is that the alpha particle comes from the nucleus of a heavier element as a decay product. It's not like we take helium gas and heat it up to drive off all the electrons. That's not an alpha particle. Right. Let's see. And the protons and neutrons in the, let's see, wait a minute. 16. Be reflected by direct contact with the nucleus. Yeah, all 3 of those are possible. So E would be the answer to that one. '17. Which one of the following statements about atomic structure is false? So 17. A, an atom is mostly empty space. Yep, it's true. Almost all the mass of the atom is concentrated in the nucleus. Yep, sure is. The protons and neutrons in the nucleus are very tightly packed. Oh yeah, they're right there as close as they can get to one another. And that brings up the question, how do you get all those positive charges together without being flying off together? That's the purpose of the neutron. The neutron stabilizes the nucleus. We're not really sure why yet. We think they exchange particles. But that's a different topic. The number of protons and neutrons is always the same in the neutral atom. No. The number of protons and electrons, yes. The number of protons and neutrons is the same in the lighter elements, in most of the isotopes of the lighter elements, but as they get bigger, you need more neutrons in order to stabilize the nucleus, because the effect of the neutron is limited in range. So you need a lot of them to stabilize all those protons. Okay, we won't go into that. That's for another time. And another course, actually. All right, 20. Which of the following atomic symbols is incorrect? Okay. So how do we deal with this one? Well, what I would do is I would take each one of them, carbon, chlorine, phosphorus, carbon, chlorine, phosphorus, potassium, and nitrogen. And first of all, before I get bogged down in all the mass numbers, I'd look at the atomic number, right? Does the atomic number match the symbol? Because they're joined at the hip. You got one. If you got the atomic number, you know the element. So carbon is 6 protons. That's true. Chlorine is 17. That one's true. Phosphorus says 15 here. Is that right? Yeah, 15 off the periodic table. Potassium, 19. Yeah, K is 19. How about nitrogen? 7 up there. What does that one say? 8. Right. That one's wrong. That's as far as you need to go. Okay, rhenium is 21. Exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus, right? That first statement, half of that statement is fluff. It means nothing to the problem. If it says rhenium-185, then that's what we need to know to answer the question. How many protons, how many neutrons? Well, let's see, rhenium. Rhenium is a transition metal. It's 75 protons. Right? So 75 protons means it's either A, B, or D. How about neutrons? 75 from 185 is 0, 1, 1. 110 neutrons. So that means D is the answer. Okay. '21. 22. Which among the following represents a set of isotopes? Atomic nuclei containing Roman numeral 1 through 5. How do we know isotopes? First of all, they have to have the same number of protons to be the same element. So number 1 and number 4 could be. Right? They got the same number of protons, different number of neutrons. So 1 and 4 would be a good pair. How about 2? Does it have a pair? 5. 2 and 5, 21, 21, and 19 and 20 neutrons each. 2 and 5. And then 3. It has no pair. 22. Oh, excuse me, it's backwards. I almost messed up. 18 protons. Well, it still doesn't matter. It doesn't have any. There are no others in there with 18 protons, so it doesn't have an isotope in that list. So the only 2 that work are 1 and 4 and 2 and 5. Correct? We can stop for a minute, let it sink in. Right? They have to be the same element. Right? So they have to have the same number of protons. And then different number of neutrons, you got an isotope pair. Right. So the answer is D, right? 1 and 4 and 2 and 5. Okay, 28. A species with 12 protons and 10 electrons. Okay, 12 protons and 10 electrons means what? It's not neutral, right? It's got 12 positives and 10 negatives, so it has an excess of 2 positives, doesn't it? Right? So we know it's a 2+ ion, so it's probably an alkaline earth, the second column. With 12 protons, that means it's magnesium. Yeah. So this is magnesium. 2+ ion. Because that tells you what the charge is. Yeah. If it's got the same number of protons and electrons, it's neutral. But if you change the number of electrons relative to the protons, you have an imbalance in the charges. If you have more electrons than protons, it's negative.
Okay.
Yes, yes, right. It's purely math. The number, let's see, 29. The number of protons, neutrons, and electrons in this ion of potassium, 19 and 39. Okay, we got them in order of P, N, and E. P, N, E. There we go. So the number of protons is 19, right? Number of neutrons would be 20. Right, 39 minus 19. And the number of electrons means it's deficient in one electron because it has an extra plus positive charge. So this would be 18 electrons. Okay. Now, let's see, we haven't got to that point yet. I'm not going to muddy the waters. We'll talk about it later. We talk about the structure of the atom in detail and writing electronic configuration. Then we'll get into some more. We'll come back to that. Okay. Let's see. 33, 34, 35. Probably goes on for a couple more. 33. Which of the following is incorrectly paired? So is strontium an alkaline earth metal? Where is it? It's in the second column. Yep, that's true. How about Ta, tantalum? Transition metal? Yep, it's let's see, where is it? There it is, 73. Yep. So that's right. F, fluorine is a halogen. Sure is. H, is hydrogen a noble gas? I don't think so. Hydrogen, well, no, not really. Right.
It's in the road.
We stick it over there just for balance. But it's not. It's all by itself. Hydrogen is an animal unto itself. Yeah.
The noble gas is still on the same rock.
Right.
How's it where?
Halogen's right next door. Fluorine, chlorine, bromine, iodine, astatine.
Well, maybe if you're talking, you ought to pick online, I can look that up and learn, because I don't really know those where they are.
The first row was out.
Should be in your review document. Look in the back. There should be one on the back
It
page.
doesn't say like those words on.
Oh, it doesn't identify them. Oh, look in your textbook. Usually in chemistry textbooks, they've got a list, alphabetical list of elements under the front cover. Yeah.
The 312 were the transition.
Boron doesn't have a name. Carbon doesn't have a name.
16 is counted. 17, how much?
Yeah.
17 is counted.
Halogens.
Yeah.
16 is chalcogens, and nitrogen group is pnictogens. The P is silent. Yeah.
What's next?
Nitrogen group. Yeah, the P is silent. Yeah, there you go. Okay, 34. Which of the pairs incorrectly was paired? Phosphorus. Is PR phosphorus? No. PR is promethium. I think it's promethium. It's a lanthanide in that bottom group. So A is the wrong one. 35. Copper, is that Cu? Yep. Carbon, that's good. Cobalt, Co. Calcium, Ca, yep. Cesium, no. Ce is cerium. Cesium is Cs. Same thing for 36. Antimony, is that Sb? That's the Latin word. Stilbium is antimony. Silicon. Yep, that's true. Silver, argentum. Argon, AR. Yeah, that's right. Astatine. Nope. AS is arsenic. Astatine is AT. Right. 37. All the following are characteristics of metals except. Well, they're good conductors of heat. Yeah. They're malleable, right? You can mold them. They're ductile. You can stretch them into thin wires. They're often lustrous if you polish them. Tend to gain electrons in chemical reactions. Metals tend to lose electrons. I don't know of a single negative ion associated with a metal. They're always positive. They lose electrons. 41. Let's see. You're given a compound with the formula MCl2. Okay? In which M is the metal, obviously. You're told that the metal ion has 26 electrons. So we got 26 electrons in that guy right there. What's the identity of the metal? Well, if we know the number of electrons, maybe we have a handle on how many protons there are. What we have to do is look at the compound. What's the preferred charge on chlorine? It's a halogen, right? It's -1. So that means there are 2 minuses for those two. That means this one metal must balance that 2 minus with a 2+ charge, correct? So if it's a 2+ with 26 electrons, how many protons does it have? It's got 2 more protons than electrons, doesn't it? So it's 28, which would be nickel. It's the nickel ion, actually. It only asks you to identify the metal, so Ni is good. 45. All right. How many oxygen atoms are there in one formula unit of Ca3PO4 2? Yep. How many oxygen atoms are in that formula? 2 times 4 is 8, isn't it? Right. Yeah, this unit, this polyatomic ion, but there are 2 of them. Right. So that means 2 times 4 is 8. Okay. How many oxygen atoms are in 4 formula units? Oh, that's not marked. Well, if we did that one, in 1 unit there are 9, correct? 9 times 4 is 36. All right, 47. The correct name for FeO. All right. First of all, is this a type 1, type 2, or type 3? What is it not? Let's put it that way. It's not a type 3 because it's a metal and a non-metal. So type 3 is out. And a type 1 is also. The difference is the charge on the metal. Is it fixed or is it variable? If it's a type 1, then the charge has to be fixed. But iron is a transition metal. And it's one of those transition metals that has multiple charges. So it's a type 2, which means what? When we name it, we have to say what the charge is because it's possible multiple charges. Right? Because iron is a transition metal. See there? 26. It has more than one possible charge. And you can see that from the periodic table. Now, there are 3 transition metals that have a fixed charge, and they would be type 1. Right, one of them is zinc, 2+, cadmium is 2+, and silver is 1+. Those you treat as a type 1 because they have fixed
And
charges.
if you don't have a charge at the top, if it's not at all.
Now, if it has multiple possible charges
Oh,
in different
More than one.
compounds, yeah, more than one possible. Now, for this compound, it's fixed, right, for the compound. But if it were in a different compound, it could have a different charge. This oxygen is a 2- charge because it's a chalcogen. They're all 2 minuses when they're combined with a metal. So that means this one has to be a 2+. So we would name it iron 2 oxide. How about this one? Just for argument's sake. It's still a type 2. If this one is a 2-, then 3 times 2- is 6 minuses, right? So if this one has to balance that 6-, then those 2 irons must balance a 6+. And each one then would have to be 3+. Right? 2 times 3+ is 6+. Okay. You don't get it?
From that information, I was like, I don't.
Well, this is not the problem.
Yeah.
I just added that.
Is there?
It's all about balancing the charges with ionic compounds.
But for O, it's always -2 because.
Yes. Right. As long as it's combined with a metal, oxygen is 2-.
Where's that out? How would I know that? But it's next to O.
Oh, look at the arrangement of the periodic table. The noble gases are always 0. Right? They don't combine with anybody. The preferred charge for the halogens is a -1. Right? Move one to the left. Move another one to the left is -2. Move another one to the left. The nitrogens are -3. And then the carbon group, it varies all over the place.
So it's like, the president is positive, or
Combine with a metal. Yeah. If you combine oxygen with a non-metal, then it's not charged anyway. Because with a non-metal, it doesn't have enough pull on the electrons to take them away from another non-metal. So what they do is share electrons. And that's why the type 3s.
Why is FE fix this? I was just thinking. Because I'm looking on it. Is this?
Well, no, oxygen is 2-.
On iron, I'm sorry. It was like
Oh, iron. It has +2 and +3. Right, those are the possible charges for iron.
Where's the
+2.
slide at all?
It's right here. Right there.
Oh, back in. Okay, I see.
Yeah, it's too small.
I was looking.
Yeah, it'll be in your periodic table. You know, and anything in useful information on that review document will be in the test. Okay. That was 47. 48. What's the correct name for Ca2+? Always remember that when we name something, according to IUPAC rules, we want it to be unambiguous. In other words, it can't be anything else. It's only that one possible name. Plus, we don't want it to be redundant. So this is calcium. And it's an ion. Right? But do we have to say what the charge is? Look where calcium is located. It's an alkaline earth. No, calcium is always 2+. So it would be redundant if we put the charge in there. So calcium ion is it. That's all you have to say. Let's see, 51. What is the subscript of barium in the formula barium sulfate? All right. 51. Barium and sulfate. sulfate is a polyatomic ion. So you got that list, you can look it up. And sulfate is a 2- charge. How about barium? Well, if barium's in the second column, right? Alkaline earth, it's always 2+, isn't it? So you only need one of these and one of those to balance the charge. Right? Because polyatomic ions, that charge is spread over the entire group. You can't separate. So polyatomics act as a single unit. That's a 2- charge, that's a 2+. So the subscript for barium would be 1. Right? You don't have to write it in because if you have the symbol, there's at least one of them. The only way there could be 0 there is if you throw it out.
So why is it 2+?
Here, because it's in the second column. Yeah, it's an alkaline earth, and they're always 2+.
Oh, but you're in
Uh,
the one.
yeah, there's just one. So the subscript would be 1. It's understood. 53. The formula for sodium hydrogen phosphate. Dihydrogen phosphate. All right, what we've got here is sodium and a polyatomic ion, dihydrogen phosphate. So dihydrogen phosphate is like this, 2 hydrogens and a phosphate. So what's the charge on it? Well, you can look it up in that list of polyatomics. Should be in the review document. Useful information. Look way at the back. Yeah, there you go. Dihydrogen phosphate. Remember, the list on the left is the same as the list on the right, only they're sorted differently. So if you're looking for the name, just look at the one that's sorted by name and go down till you find the D's. Dihydrogen phosphate. So what's the charge on it? Right, -1. That's a +1. That's all you need. 1 sodium, 1 dihydrogen phosphate. So the answer there is 53, is A. All right. The only way to get comfortable with these is to do a lot of them and get your brain clicking in that direction. If you just try to learn the rules on things and hope that you can remember them for an exam, it's going to lead to disaster. You got to practice it. Did you find it? Okay. 56. I think it was A, wasn't it? 56, which is incorrectly named. 56. All right. It looks to me like we're naming acids here. How do I know? Well, we're leaving out the aqueous part. We have to assume that they're in an aqueous solution. But they're acids because they start with hydrogen. Okay, how about H2SO4? Is that sulfuric acid? What's the first thing you look for after hydrogen? Right? You look for hydrogen for the acid. And then to name them, you look for oxygen. If there's oxygen, you don't say hydro. You just look at the non-hydrogen part of the molecule. SO4 is sulfate. H become X, so it's sulfuric acid. That's correct. How about the second one? Right? No hydro there, right? Because there's oxygen. CO3, what is that? Carbonate, yeah, carbonate. So H become X. Huh? Carbonate. That's just the name of it. Now, first of all, if there's oxygen, you don't say hydro. You go to the polyatomic molecule of the polyatomic ion. What's its name? CO3 is carbonate, and then H become X. So it's carbonic acid. Okay. How about the H3PO4? Right, no hydro there. PO4, what is PO4? Phosphate, 8 becomes X, phosphoric acid. HCN, no oxygen. You should say hydro there, hydrocyanic acid. Right, so D is wrong. And E is correct.
What are those just like? Those aren't all the body right?
Oh yeah, they are.
They are?
Uh-huh.
Okay, that's what I want.
Yeah, they're all in there. Which of the following name is correct? All right. Well, let's see. 59 is sulfide linked. Is it the same as S2 minus? Yeah. Right. It's in the oxygens group, so it has a 2 minus charge. Right. Oxygen, sulfur, selenium, tellurium, those are all 2 minus charge. Right. So that's correct. Sulfide names the ion. How about ammonium chloride? Is that right? Yeah. NH4 is ammonium, and Cl, the second part, the anion part, is chlorine, but we changed the ending to "ide." Ammonium chloride.
Wow.
Because it's the naming convention. Right. The second one, yeah, the anion, you change the ending to IDE, unless it's a polyatomic. If it's polyatomic, then you just stick with the name of the polyatomic ion. But if it's one of the elements, one of the non-metal elements in a combination like this, then you change the ending to IDE. How about C2H3O2? First of all, is that an acid? Yeah. So that means what's attached to the hydrogen? C2H3O2. Hydrogen. Starts with hydrogen. What's C2H3O2 is what? Sorry? It's the acetate ion. So H become X. It's acetic acid. Okay? 5% acetic acid is vinegar. So that's what you swallow when you put vinegar and oil on your salad. Yeah, that's correct. How about BaO? Ba is barium. Oxygen would be oxide. Barium, they're all right. Yeah, all 4 of them are correct. All right, I'm going to leave myself with just 1 hour to get this last thing done. Looks like. All right, rather than draw this one on the board, we're going to have to go from. It's better if I can draw it on the board, but we don't have time. So what are we looking for here? The blue, well, the ones with red in them. Those are the ones that should be empty. If you see something like this on an exam, those will be empty, and now we need to fill them out. So if you have the simple 206 Pb, right, we know that's lead, and we know the mass number is 206. How do we know the number of protons, the atomic number? Look it up. Pb. Right? Pb is 82. Right there, see, 82. That's the number of protons. So you use your periodic table to find that information. The number of neutrons would be 206 minus 82, which is 124. How about the number of electrons? Yeah, this is a neutral atom, right? There's no charge on it. So they have to be the same. And then net charge is 0. Okay. All right. Now for the next one, the symbol is missing. So we look at 31 protons and find out what the symbol should be. Yeah, Ga, gallium. So you got the symbol, but we might need a charge. We look at the number of protons. Oh, the net charge is given, right? So it's 3+, Ga 3+. Yep. Right. 28 electrons will give us 3 extra positives. Yep. How about 52 protons? I have to look at it. Te is tellurium. I don't know if you had to memorize that one, but and then we've got 52 protons and 54 electrons. So what's the net charge? Yeah, right. You got 2 extra negatives. And so you would say Te2 minus. For the last one, protons, we look at the symbol for manganese and we see it's got 25 protons. Right? It's got a 2+ charge is given to you. So that means the number of electrons would have to be 23. We have 2 less. We have an excess of 2 pluses. And that's it. The next one is along the same lines, right? So we don't have to stop here. Memorize your symbols, like silver is Ag, calcium is Ca, iodine is I, copper is Cu, phosphorus is P. Then we write down the names for these compounds, and you have to decide, are they type 1, type 2, or type 3? Right. First decision is, are they type 3? Is it non-metal, non-metal? Right. If it's not non-metal, non-metal, then you got to go to find out, is it a 1 or a 2? That's where you look at the metal. You say, is it a fixed charge? Is it part of the first column, the second column, or the boron column? All right, boron, aluminum, gallium, those are all 3+. If it's any one of those, then it's a type 1. And you don't have to say what the charge is. Right? It's just a fixed charge of +1, +2, or +3. But in this case, iron, we have to determine what is the charge on iron to make a type 2 compound. Sulfate is 2-. It's a polyatomic ion. That means that one iron has to be a 2+. So we name it iron 2 sulfate. Okay. Believe it or not, this is the easier system. When I was in school, we had to learn iron 2 was ferrous. It would be ferrous sulfate. Right? If it was iron 3, it would be ferric. If it was copper 1, it would be cuprous. And if it was copper 2, it'd be cupric. Right? Oh. But that's a mess. Oh, C2H213. Yes, it's acetate. That's the acetate polyatomic ion. Yeah. If you've got a compound with a metal and the non-metal has an element and oxygen in it, then you're pretty sure it's polyatomic. The only exceptions to that are things like cyanide, which has no oxygen in it, but it's a polyatomic.
So, potassium nitrate is also
Nitrite. Nitrite. Yeah. Watch out for those subscripts. NO2 is nitrite.
Sheet, right?
Yeah.
So we'll have it on.
NO3 is nitrate. NO2 is nitrite.
That's on. We'll have it.
Yes, it's a polyatomic. It'll be in that list. Calcium is a 2+ ion. It's an alkaline earth. Hydroxide is a polyatomic with a -1 charge. So if it's only -1 and calcium's a +2, you need 2 of them. Right. So calcium hydroxide is all you need because calcium is a fixed charge. How about NiCO3? What's CO3? It's a polyatomic, isn't it? Okay, and it's charged. We did it before. 2-. 2-. So nickel has to be a 2+. So nickel 2 carbonate is correct. Best way to memorize them is to use them. Use them a lot. Okay, we still got some more here. The nitrate ion, that's yeah, sure. Back up.
Yeah, it says that carbonate for the last carbonate is +2, and then so nickel would have to be.
No, wait a minute. Carbonate should be -2. Does it say +2?
Yeah. Oh no.
Okay.
Mhm. Okay.
Yeah. Oh, the way to avoid making that error, there's only one polyatomic in there that's plus.
Oh, right.
Remember which one it is? Ammonium, right? That's the only one. The rest of them are all negatives. Okay. So this one's kind of hiding up underneath the highlighted thing. Nitrate ion is NO. Ooh, that's wrong. Nitrate is NO3. And that should be, hold on a second. I think I can do this. Nope, that's not it. Oh, here we go. Yeah, there we go. I need to subscript it. There we go. So NO3 minus is the nitrate ion. Let me save that. The charge is hidden up underneath that highlight. NO3 minus is nitrate ion. How about aluminum oxide? Right? Aluminum is over there underneath boron. It's always +3. So it makes a type 1 compound. Oxygen is -2. Aluminum's a +3. So you get them to balance by cross multiplying. You bring the charge of aluminum over subscript of oxygen and the charge of oxygen subscript of aluminum, and that gives you a 6+ balanced against a 6-.
So why would it use what order is it used?
Where? Because it's the easiest way. I mean, you can do it like this. You got aluminum and oxygen. Oxygen is a chalcogen, it's always 2-, right? Aluminum is a fixed charge of 3+. See? So how are you going to get an odd and an even to come out balanced? Right. You have to make both of them even. So if you I'm sorry. Right. If you multiply this one times 2, it makes it even, right? Multiply anything times 2 and you got an even number, right? Okay. So 2 times 3 is 6+. And 2 times something else needs to be a 6-. Right? So it has to be a 3. That's the best way to do it. And that's why I say, I'm sorry. No, it's just 3. Right? A subscript of 3 means you got 3 oxygens at 2- each.
But if you're trying to counter the positive 30 the aluminum, why would it still be a positive?
Well, you got 2 aluminums, right? Right. You got aluminum 3+, and you got aluminum 3+. And then you got an oxygen 2-, and an oxygen 2-, and an oxygen 2-. So these two together are a total of 6+, right? And these 3 together are a total of 6-. That gives you balance. They neutralize each other.
Oh,
yeah. I don't know why I haven't done it that way before. Whatever works, right? Yeah. Okay. Let's see. Nitrate aluminum oxide, ammonium ion. We talked about that one already. NH4+. That's a polyatomic ion. That's the only positive one in the group. Perchloric acid. Right? Has to start with H. But we look at what is if eights become X, then when you go backwards, X become eights. And that tells you what the polyatomic is. Perchlorate. So you look up perchlorate in your list, and it's ClO4-. So H, ClO4, you only need 1 hydrogen because it's the positive, and the ClO4- is the 1-. 1 hydrogen, 1 perchlorate, and you have your formula. Are we good? Think about it while I fill my drink. You know, the flavored waters you get in the store are just way too weak. Right? So I get water, whatever is available, and then I get my thing of Mio, and I really slap it to it. And it holds up really good with ice. You know, as the ice melts, it doesn't water it down so much. I had a teacher at Georgia State University. He was my biology professor, advisor. And on the side, he had a piece of property outside of Atlanta and had a lot of different types of terrain. He had some pasture, and he had some woods, and he had some rocky outcrops. And he had a creek running through it, and he had goats. He used his goats to generate monoclonal antibodies. He had a business on the side. But he used to walk around his property, and in Georgia, it gets pretty hot in the summer. So you want a cool drink with you. Well, he made his own beer. And when he made it, he made it in this big glass jug. And when it was ready to bottle, he put it in the bottle, and then he threw a little extra sugar in with it. So it continued to ferment. And I guess he had to experiment with it, because if you build up too much pressure, your bottle will blow. But instead of, let's see, what's the, I was trying to think of the alcohol composition. Alcohol by volume for beer is 6.4. I think it's 6.4%. Well, he put a little extra sugar in there and boosted it up to about 15%, more like wine. And he did that so he could take his beer and put it in his cooler, right, with ice, and the ice would melt, and it would water it down some, but not enough to destroy the taste. And he'd walk around his property with that beer. And it was good. He made some good beer. I mean, I'm not a connoisseur, but it was dark beer. Yes. Mm-hmm. Look at the alphabetical list for the names. Do you see the P's down there? Perchlorate. ClO4 minus. Just add a hydrogen. Yeah. And then copper 2 bromide, right? Copper can have a multiple charge, either a 1 or a 2. So it has to be a type 2 compound. You know you got bromine, you know you got copper, so you write those in first. And then you say, let's do it that way. You write in your copper, you know it's going to be copper, you know it's going to be bromine for the bromide. Bromine is always a -1. And the copper, it tells you right there, the copper is a 2+. So that means you need 2 of these to balance the charge.
So we start one with the copper percent 1. Or whatever.
Yeah, if it was a Roman numeral 1, yeah, it would just be 1 and 1. Yeah, correct. All right. What else? More names. Is that the last? No, we got more. Oh, okay. I'm going to have to cut it off here. Let's scroll there. Okay. Get that on the recording, and then go down a little further and get that on the recording. Oh, okay. Right. So there's the top one. Got it. Okay. And then we'll scroll a little more. You got that one already? Yeah. Okay. Then we'll go down to the next one. There. And then we'll go catch the rest of them right there. I wanted to point out that acetic acid, the way my textbook and your textbook report acetic acid is HC2H3O2. And that's fine, right? That's a valid molecular formula. But you may see it this way also. It's the same number of oxygens, carbons, and hydrogens, but it gives you a little more information about the structure of the molecule. This CH3 is like this, with hydrogens, right? And then this carbon is cooked to that carbon. And then these two oxygens are like this and like this. Right? And this is the acid hydrogen. That's the one that dissociates and makes the acid solution. You don't have to remember that for any of the tests or anything like that. I just wanted to show you in case it cropped up in the future.
So where the C one doesn't, or if you did use the C one, where it doesn't start with an H, how would you know it's an acid?
You recognize this group right here.
Right.
This is known as a carboxylic group. Carboxylic acid group. The hydrogen's on the other end. For our purposes, I'm only going to show you the kind where you start with hydrogen. Okay. And then the last one, law of definite proportions. Definite proportions just says no matter where the compound originated, once you determine the ratio by mass of the elements in a compound, the origin doesn't matter anymore. If you've got a compound here, got a compound there from different origins, they will always have the same definite proportions by mass of the elements. And that was Lavoisier. Oh, sorry. That was D. Yeah. Okay. This one, law of multiple proportions. Oh, we've covered that one before. B, the mass of oxygen that is combined with a fixed mass of nitrogen in each of the binary nitrogen oxides can be expressed as a ratio of small whole numbers. So you're increasing the amount of oxygen, right? Yeah, the amount of oxygen with each successive compound. And the ratio of those oxygens by mass is whole number multiples. Which one's not from a Latin name? Iron is Fe, copper Cu, sodium's Na, potassium's K, and titanium is Ti. So A through D are all Latin derived and titanium's not. Yeah, because the symbols, right? If the symbol bears no resemblance to the English name, it's got to be Latin, right? Potassium's K, sodium's Na, copper Cu, iron is Fe. Which of the following is not likely to form from the appropriate atom? So you look from where it's at, and you also look at your periodic table, because some of these, one of them is a transition metal, titanium. So you look at titanium and see, is this allowed in the charges that are next to it in the little square? You'll have a periodic table, so you can look that up. Sodium is an alkali metal. It's always +1. Magnesium is an alkaline earth. It's always 2+. That's correct. Arsenic is a pnictogen. It's in the nitrogen group. It's always a 3-. It's allowed, in other words. Carbon, not likely to form a 4+. In order to do that, it would have to lose 4 electrons. Now, that doesn't mean it doesn't occur, but it's not likely to occur compared to the rest of them. Okay, that's the key. Not likely. Protons, neutrons, electrons in this anion. In the anion formed of 125 iodine. That's the key. It says it's an anion formed from this. So how do you form it from that? Well, it's iodine, so it's going to be a -1 charge, isn't it? It's a halogen. Now we can go ahead. Iodine is 53. Right? So the number of electrons have to be 54. Protons, neutrons would be what? 72 neutrons. So D is the answer. 5474. Excuse me. 52, excuse me. I was looking at the wrong one. 53, 72, and 54. D is the best answer. My goodness, when is this ever going to end?
Is it on 5 on pages?
No, this is like this.
Okay.
This is
I don't even have all that.
Which of the following atoms, isotopes, or ions contain 23 protons, 18 electrons, and 27 neutrons? 23 protons tells you what symbol it is. Vanadium, right? V. So it's either C or E. What we have to do is say, okay, with that many protons and 27 neutrons, it would be 50 mass number. Both of those have 50, C and E. So we have to look at the charges. What are metals most likely to do? And as evidenced by 23 protons and 18 electrons, it would have an excess of 5 positive charges, wouldn't it? Right. So C would be the answer. Which of the following compounds is incorrectly named? All right. Do you have to say magnesium dihydroxide? No, because magnesium is 2+, hydroxide is a -1. You have to have 2 of them. That's redundant. It's also trying to turn a type 1 compound name into a type 3. So you don't do that. And the rest of them are correct. Huh? A is the wrong one. You don't say dihydroxide. Now, if we had had this, right? Right, that's a non-metal, so it'd be a type 3, and we would name it dihydrogen monoxide, right? Type 3 compound. But we don't do that, right? Because this is water. Okay. So now I need to close this document. Yeah, close this one.